He sent me information regarding our rooms, so we're ready to go next week. I forgot the rooms, so I'll tell you on Monday. If my memory's right, we're in Turlington, not far from here. Now then, BLAB Chem continued. Let's finish first. Remaining consideration we have in the notes about indicators. And then we charge in the buffers. This is question 35. Yep. Last time we looked at the critical data for indicator HGX, from which we determine Ka for HGX, 2 times 10 to the minus 2. Since at a pH of 1.7, HGX is 50% ionized. So at that midway pH, the pH at which indicator HGX showed green, a mix of equal quantities of yellow with blue, KaHGX is equal to the hydronium ion molarity at that pH. That hydronium ion molarity is 2 times 10 to the minus 2 for pH 1.7. The question then said, if we take a solution of HQ, another mythical acid, treat it with this indicator, and see a distinct yellow-green color, for which our color code information last time from HGX told us the pH is on the order of 1.3. Calculate the numerical label on the bottle for the HQ solution. M sub I for the HQ solution. Well, in our mind's eye, we're seeing the equilibrium reaction. HQ plus water, double arrows, hydronium ion plus Q minus. A single solute solution. So for that solution, hydronium ion molarity, Q minus molarities are equal. So the the x squared over m sub I minus x recipe applies. And at the distinct yellow-green color observation, for which the pH is 1.3, the corresponding hydronium ion molarity is 5 times 10 to the minus 2, which means the Q minus molarity is also 5 times 10 to the minus 2. So, there's the chemical version of the equilibrium constant expression, containing m sub I, which is what we want to compute. Here we put in the numbers, do the arithmetic. That's it. 1836. Just to try to be sure that you remember what Ka values measure. Bronsted-Lowry acid base strength. So, question 1836, if mythical acid HC is twice as strong as mythical indicator HGX, since KaHGX has been found to be 2 times 10 to the minus 2, KaHC is 4 times 10 to the minus 2. Twice as strong. So its Ka value is twice that for HGX. Now we go to buffers. The first battery of information, which I've scrawled on the board, is in the notes. But it's important. It's important so that you have a conceptual feeling, a conceptual appreciation for buffers. What they are, what they do, how they're prepared. You ever heard of blood? Ever heard of sweat? Ever heard of tears? Famous rock group back in my day. But for all time. Blood, sweat, and tears are examples of very important human buffer systems. Happy human blood, for example, buffers at about a pH of 7.4. optimum pH. It's a bicarbon H2CO3 buffer. Shouldn't be surprising to you, since CO2 is one of our respiration products. In a short while, you'll know how to calculate that value. Don't worry about that now. Buffer. Simplest definition, a buffer is a solution which is designed to maintain, preserve pH. Like blood. Because if blood pH drifts above 7.6, you suffer from a condition called alkalosis. If it drifts below 7.2, you are affected by a condition called acidosis. There was a movie about this. Anybody remember the movie? Nobody remember? I'm trying to recall the title myself. Let's see. Something Syndrome, I believe.
Who was in it? Who was in it?
I don't remember. The people in it were not anybody that you'd know straight away. It was kind of a grade B quality movie. But it was interesting because it reflected on a town where all the townspeople, after this strange thing landed from outer space, all the townspeople died, with the exception of two people. An old guy who was a drunk and a baby who was sick. And the people who were brought in to study this found out that what this mysterious thing that came from outer space thrived on was happy human blood. But if the pH of the blood was above 7.6, this killed this thing. The pH of the blood was lower than 7.2. It killed this thing. That's why the drunk was still alive, because he was drinking Sterno, so his blood was pretty basic, and the sick kid had too much CO2 in the system. So the system was too acidic, kept them both alive. That's the chemistry of the situation. It was interesting from a chemistry standpoint. I'll think of the name sometime and tell you. In any case, it's common that we buffer within the range of 3.0 to 11.0, mildly acidic up to mildly basic. But you can buffer at pHs above or below the pH values at the boundary for this range. If you wanted a buffer at pH 0.0, what would you do? You want to preserve pH at 0.0. You fill up your bathtub with 1 molar hydrochloric acid solution. Isn't that pH 0.0? And if you got a bathtub full of it, you got a whole lot of 1 molar hydronium ion. You want to buffer at pH 14.0? This time fill up your bathtub with 1 molar sodium hydroxide solution. Now I advise you strongly don't take a bath in there. But if you want to do chemistry in there and maintain pH at 14.0, that'll do a good job. Common buffer preparation. In the same solution, we select a weak acid and its conjugate base. Acetic acid and a source of acetate ion like sodium acetate or potassium acetate. Ammonium chloride as a source of ammonium ion and ammonia. Dissolve the acid and its conjugate base in the same solution with the acid solute and the conjugate base solute each being present at high molarity. Bingo, you just made a buffer. We'll look at examples why that works as a buffer in a moment. Now, is this Okay, here. Now, well, let's look at it right now, why this is a buffer, if you have this high molarity of acid and base. Okay? Let's imagine I want to change the pH of an acetic acid acetate ion buffer. Adding hydronium ion, the most obvious way to change pH by making pH come down, or add hydroxide ion, attempt to change pH by making the pH go up. Nothing fancy about that. Add hydroxide ion or a source of hydroxide ion. Add hydronium ion or a source of hydronium ion. Well, in your mind's eye, do you see the composition, the PSI for the acetic acid acetate ion buffer? If you put hydronium ion in there, or if you bubble in HCl. If you bubble in HCl, will the HCl react with water to make hydronium ion? Because if it does, the pH is coming down dramatically. But your knowledge of chemistry at this stage of the game tells you, if you bubble HCl through an acetic acid acetate ion buffer, what will the HCl in fact react with?
Acetate ion.
Acetate ion. Isn't that the strongest base and high molarity in the pot? Absolutely. So HCl reacts with acetate ion, makes more acetic acid and chloride ion. Have we made hydronium ion by adding HCl? No. Buffer. Want to make the pH go up. Add sodium oxide. You add sodium oxide to water. Hey, oxide ion reacts with water, extend 100%, and per mole of oxide ion reacted, you make 2 moles of hydroxide ion. Woo! So let's add sodium oxide to the acetic acid acetate ion buffer. But in this case, will the sodium oxide react with water solvent? No. What will it react with? The acetic acid. That's the principal acid in the pot. And the acetic acid will react with the oxide ion and make acetate ion. So you wind up not making hydroxide ion. You wind up not changing the pH much at all. All right? Now, the buffer system described in the notes is the acetic acid acetate ion buffer. If I have a solution containing acetic acid and acetate ion at the same molarity, say at the same high molarity, say a solution that's 1 molar acetic acid, 1 molar acetate ion. Have you had any experience with a solution like this?
Yes.
Where? When? Lab, assignment 1. Last part of assignment 1 in 46L. You think I'm trying to get 46L connected with what we talk about in class? You're damn right. Because if you want to understand this stuff, lab and lecture has got to fit together. Now then, acetic acid acetate ion buffer, with the acetic acid and acetate ion each being present at high molarity. Is this buffer solution acidic, basic, or neutral? It's acidic, isn't it? Why is it acidic? Why is that solution acidic? Acetic acid acetate ion buffer. Why is that solution acidic? Ka acetic acid, 1.8 times 10 to minus 5. Kb acetate ion, 5.6 times 10 to the minus 10. Acetic acid is far more effective at reacting with water to create hydronium ion than acetate ion is at reacting with water to create hydroxide ion. Upshot, solution is acidic. How about this system? Now let's make a buffer by putting together 100 milliliters of 1 molar ammonium chloride solution and 100 milliliters of ammonia solution, 1 molar. When we make this mix, what will be the ammonium ion molarity? You recognize, for starters, that the ammonium ion molarity and the ammonia molarities will be the same, practically speaking. What is the molarity value? I'm listening. I'm listening. 0.50. Yes! If I charged you folks $1 for each time you mutilated significant figures, I could buy a mansion at the end of the week. Don't do that. Is this buffer acidic, basic, or neutral? What is it?
Basic.
Basic. Because here, Ka for the acid, 5.6 times 10 to the minus 10, equal to same value as Kb for acetate ion. Serendipity. It's just one of the things Mother Nature did. No explanation for that. And Kb ammonia, 1.8 times 10 to the minus 5. Just like Ka acetic acid. Okay? Serendipity. But here, Kb value, much larger than Ka value, so this is a basic buffer. Now then, for this buffer, the ammonium ion ammonia buffer, what is the principal Bronsted-Lowry acid-base equilibrium reaction in this buffer solution? You know how to play the game. You pay attention first to what? PSI. If you don't know what's in the system, you cannot deal with its chemistry. And from the PSI, you recognize the strongest acid in abundance is ammonium ion. And the strongest base in abundance is? Ammonia. So, for this solution, the principal Bronsted-Lowry acid-base equilibrium reaction is ammonium ion plus ammonia to produce, guess what? Ammonium ion plus ammonia. Now, that leads to no net change in system composition, no net change in chemistry of the system, and does not give us a handle on hydronium ion concentration. Consequently, does not give us a handle on pH. So if we want to get at, which is arguably the most important property of a buffer, namely solution pH, we got to go someplace else. Where's the someplace else we go for this system? Can we use Ka ammonium ion? Is ammonium ion a main ingredient of this system? Can I use Kb ammonia? Is ammonia a main ingredient of this system? Absolutely, I can use either one. It doesn't make any difference. Makes no difference at all. So those would be equilibria that we could use to calculate pH for that buffer. Now then, a little bit of buffer arithmetic. Hypothetical acid HX, solution thereof reacts with water, equilibrium established with hydronium ion X minus. So if I have an HX X minus buffer, I can use this equilibrium to get a handle on pH for that solution. As soon as I hear pH, I've got to have an equilibrium reaction which involves hydronium ion or hydroxide ion, period. Okay? And I can also use this, because X minus is also a principal ingredient of this system. This gives me a direct handle on hydroxide ion. Since I'm usually interested in pH rather than PHO, where pH is negative log to the base 10 of the hydronium ion concentration, abbreviational reference, and PHO is negative log to the base 10 of the hydroxide ion concentration, I'll use this equilibrium and deal with Ka. I don't have to, but for my own convenience, because this goes directly to pH, whereas that I need one more step to get to pH. So I write Ka, and then I recognize by doing some logarithmic arithmetic that log to the base 10 of KaHX is log to the base 10 of hydronium ion molarity plus log to the base 10 of the X minus conjugate base of HX molarity minus log of the equilibrium molarity of ionizing solute HX. Now I'm going to take this expression and rearrange it ever so simply. I'm going to take the log hydronium ion term, put it on this side of the fence, and the log Ka term, put it on this side of the fence. So now I got minus log hydronium ion molarity is log X minus molarity minus log HX molarity minus log KaHX. Well, we know what this is, don't we? This is pH. So what I've done is to show you how this analysis gives me an immediate direct handle on pH. But if you want this immediate direct handle on pH, you've got to use logs. So for me, I'll usually stick with this, not this. But it doesn't matter, as long as you do the arithmetic correctly. And negative log to the base 10 of Ka is pKa. And a small letter p, that means negative log to the base 10 of. That's what it means. So this converts to this. And please, in doing arithmetic, if you want to use this logarithmic form of an ionization equilibrium involving an acid to get at pH for a buffer solution, take note that this log term is not equal to this. Now then, this also leads us to another very important realization regarding buffers. Here's our general expression for a solution which contains how many principal solutes that affect pH. If I'm going to use this expression to get hydronium ion molarity or hydroxide ion molarity for an acid solution or a base solution, how many solutes are present in the solution if I'm going to be able to use x squared over m sub I minus x? How many solutes of consequence are present in the solution which affect pH? How many? One and one only. So this recipe is no good for buffers. Because in a buffer, I got the acid and its conjugate base at high concentration. I got two solutes of consequence. So x squared over m sub I minus x does not apply to buffers. Okay. Now let's do some calcs. 1838. Back to an ammonium ion buffer. I guess I could have stuck with that, but just to parallel what's in the notes, we'll stick with the 100 mils of 0.80 molar ammonia and 100 mils of 1.0 molar ammonium chloride solution. And consider treating this mix with 0.020 moles of HCl gas, after which we want to calculate pH. But before we imagine putting in the HCl gas, before we proceed with this part of this question, how do we get the how do we get the pH for this buffer? Well, again, I prefer to use the non-logarithmic analysis. So I'm going to write Ka, ammonium ion, is 5.6 times 10 to the minus 10 equals hydronium ion molarity times ammonia molarity divided by ammonium ion molarity. Remember, we have not yet considered adding the HCl gas. Next question. Or maybe let's put it as a directive. Please, when you do problems like this, don't do unnecessary arithmetic. Point. When I make this mix, what will the ammonia molarity become? What will it become? 0.40 molar. Am I not going to dilute this solution by a factor of 2? And the ammonium ion molarity will become 0.50 molar. So I can put in here 0.40 molar, 0.50 molar. So 0.40 divided by 0.50. 0.8. Multiply this by 0.8, and I got the hydronium ion concentration. Okay? But I could have put it to 0.8 and the 1 here straight away, because it wouldn't change the ratio, would it? Okay? Now let's go to the second part of the puzzle. You can do the arithmetic if you really want the hydronium ion molarity. We tell you how to get it. We're now going to imagine adding the HCl gas. This will cause a chemical change in the system. And the best way to represent a chemical change is to do what? Write the equation for the reaction that corresponds to that chemical change. And how do we write this equation for the reaction? PSI. PSI, you're damn right. All right? Now also keep in mind, when I write a reaction equation, I have a relationship involving moles, not concentrations. So let's go back to what we started with here and decide how many moles of ammonia and how many moles of ammonium ion we begin with. How many? How many moles of ammonium we got initially? Moles of ammonia.
0.080.
Ammonium ion, 0.10. Now comes the HCl gas. We've got our PSI on the board with the exception of water. But we don't really need to consider water at this immediate moment because when we add the HCl to this system, with what will the HCl react? Ammonia. Much stronger base than water. And a principal component of the system. So we go with this. What would you like to tell me about the extent of this reaction? Tell me, to what extent does HCl react with water? 100%, doesn't it? Is ammonia stronger base than water? Well, damn it. If HCl reacts with water extent of 100%, and ammonia is a better H plus grabber than water, you can bet this reaction goes 100%. That's the understanding the chemistry part. That's what we want. Now let's do some numbers. The quantitative aspect of PSI. By this reaction, how much ammonia did we murder? 0.020 moles. How much ammonium ion did we make? Boy, that's tough. 0.020 moles. Killed. Make. So now, to calculate pH, or hydronium ion concentration, I go back to this and recognize that the change that I have made to this system is in fact to have changed the ammonia to ammonium ion ratio relative to what I started with. What is the ratio now? At this point, after I added the HCl, how much total mole ammonia do I have in the pot? 0.060, right? I had 0.080, I killed 0.020, so now I got 0.060. How much ammonium ion do I now have in the pot? 0.12 moles. Now, are these Molarities? Can I use them in here? Should I take this value, moles, and divide it by 0.20 liters, and this value, moles, and divide it by 0.20 liters, which means I'm doing the same arithmetic top and bottom, and I'm wasting my time. So I'm not going to do that. I'm going to let this thing talk to me. I'm going to let it tell me what it means. That's what you have to do. Don't do unnecessary arithmetic. In certain cases, you may have to convert to concentration, but not this time, because dividing top and bottom by the same value was not going to change the mole ratio or the molar concentration ratio of ammonia to ammoniumine whatsoever. So guess what? The hydronium concentration is now this. Twice this, pardon me. 2 times this. Well, I haven't changed hydronium concentration very much. Now take note of how I can modify this problem. What would happen to this system if I added not 0.020 moles of HCl, I add 0.080 moles of HCl? Would I now have clobbered all the ammonia originally present? Well, what I do now to calculate pH? Would I now have a single solute system? Because now, after murdering all the ammonia, by adding just the right amount of HCl to murder all the ammonia and convert it to ammoniumine, now I can go back to x squared over m sub I minus x. Because now I really have a solution of ammoniumine. That's it. Fair enough? All right. What if I choose to add, because I can make any damn mixture I want in the lab. I can do anything I want in the lab. Blow up Gainesville. Let's add 0.10 moles of HCl. Now what's going to happen? Will I kill all the ammonia? Yes. And in so doing turn all the killed ammonia into ammoniumine, just like before. But after killing all the ammonia, I still will have a residual 0.020 moles of HCl, won't I? Will that react with something else in the system? Yes. What's the something else? Water. And if 0.020 moles of HCl is dissolved in 200 milliliters of water, I will in fact have 0.020 moles of hydronium ion, because I know the HCl reacts with water extent of 100% to make hydronium ion, over a total solution volume of 0.20 liters. What molarity of hydronium ion will this give me? You accept that? In this solution, after I did this, will I now give a damn about ammonium ion being in there to get pH for the solution? Huh? Will I now care about ammonium ion being in there? You think ammonium ion is going to make a measurable contribution to the hydronium ion molarity in this solution? Hell no. Do the arithmetic to convince yourself, and we'll proceed from this point next time.